high impedance grounded three-phase systems. In this presentation, we're going to be looking at solidly or low impedance grounded systems because we need to have a bit of an idea as to why we even have a choice. High impedance grounding operation and high impedance grounding components. The majority of electrical installations utilize solidly grounded sources. This means a continuous low impedance path to the ground electrode. It is cheap and effective. During a ground fault, very large currents will flow from the affected line conductor to ground and back to the source on the ground conductor. The larger the kVA of the system, the higher the fault currents. And as systems get larger and larger and larger, because we use more and more electricity, we tend to get more extreme situations. So with a solidly grounded system, we can get damaged equipment due to excessive magnetic stresses caused by the huge flow of current. We can have insulation damage, which can then lead to line-to-line short circuits. And we can also have significant arc flash and arc flash situations, which can then result in personal injury. In other situations, if the source is actually a generator, further damage can occur, and that's because the generator will attempt to supply the high fault current to the circuit, leading to a runaway condition of the rotating assembly, and this can cause damage to the generator. Arcing ground faults draw low-level currents, and this can cause significant damage due to the heat generated. If the current flow is too tiny, it means that the overcurrent will never trip, even though there is significant damage taking place. So only 2 amps flowing, but causing a intense heat event in one particular location, if the conductors are inside a metal conduit, at some point, if only one of them is ground faulting, it may cause damage to other adjacent conductors in the conduit. And if that were to take place, the longer an arcing fault exists, the more likely it is that insulation will be damaged between two line conductors in close proximity. This leads to a full line-to-line short circuit, and of course, significant damage. And at this point, yes, the overcurrents would both trip. In a high impedance system, a large impedance device is connected in series with the ground conductor of the system. Resistors are typically used. However, on high voltage systems, inductive reactors are sometimes preferred. And so we can see that resistor outlined in red. It often looks like a humongous three-phase toaster or some humongous toaster or heating element. It's usually situated outdoors because when current flows through it, it's going to generate a significant amount of heat. During a ground fault, the current magnitude is restricted by the ground impedance, and that's because of Ohm's law. The overall equipment damage is eliminated due to low ground fault current. The overcurrents do not trip, as the current is typically restricted below 5 amps. Any arc blast or flash is eliminated during the ground fault event. All this looking pretty good. The voltages remain stable, and it provides protection for generators. Now, of course, we're still left with the possibility that if two ground faults were to develop, a line-to-line short circuit would then result. And of course, that would be bad, and we would have the same form of destructive force as what we saw in the solidly grounded low impedance system. But at least what we're doing here is we're reducing the risk to personnel with arc flash and blast. And if we're really quick and we're attentive, we can go and find the ground fault before there is a significant line-to-line short circuit. Now, in a high impedance grounded system, typically what we have is a control module as well as a CT, and the CT is mounted so that the conductor that goes to the resistor goes through the CT. The ground must be monitored, and if a ground fault is present, an alarm will be initiated through lights or horn or something of that nature. Then it is a race against the clock. You want to try to fix the ground fault before a second ground fault develops, because you don't want a line-to-line fault. But what if the resistor breaks or fails? I mean, that would be really bad because we know that voltages on the individual lines of a Y system could then be affected. So you really don't want that to happen, or if it does, you want to know like right away. And in order to accomplish that, what we typically have is something called a sensing resistor. So the sensing resistor connects with a ground terminal as well as a wire that connects to the top of the resistor. And it connects back to the control module. And its purpose is to continually verify that the resistor is intact. Now, the way it does this is actually quite clever. It sends a very small pulse of DC into the ground, and then it reads the current back through the NGR. If it senses there's current, it means that the NGR is intact. If there's no current, it means the NGR is broken, and it would immediately initiate an alarm. Impedance or high impedance grounded systems are also covered a little bit in Section 10 of the Canadian Electrical Code 10300, as well as a few diagrams in Appendix B.